Okay, so for this section, we are talking about the directional derivative. So we want to do it really systematically, but for the figure, we want to look at the figure that we established in 15.3. Well, actually, that's the sequence of figures, so that's the figure that we want. Okay. So basically, we have seen that for the partial derivative in this picture is in terms of x. This is a partial derivative in terms of x that we are treating y as a constant. Right? So we mentioned that okay, that will be the slope of the tangent line of the curve being purple. But there's another way of doing the interpretation. So if you recall, so here we have this elliptic paraboloid, which is called z equals to 4 minus x squared minus 2y squared, right? And here, essentially, this slope of the tangent line right here, this is the partial derivative, and basically this is del z del x. That's something we have done. This is the negative slope, but then that's essentially the slope of the tangent line that's just going along this direction. So that now we know that, so we don't really need the line right here. But we want to indicate that this curve is a curve. If you want to do the parameterization, this is just we fix y as a constant 1, right? And then we are just changing x. So if you increase x from the black point, it will go this direction. If you decrease x, it will go this direction. Okay, so you can think about this as a parameterized curve. Okay, so this is a curve C. So in this situation, we have y as constant 1. Z is now just the function evaluated at y equals 1, which is exactly 2 minus x squared. Okay. I probably want to put it in another system of equations. So that's equivalent as saying my z has to be 2 minus x squared and y must be 1. Here, so the slope of the tangent line in black on the right hand side figure, that's the interpretation of the partial derivative, right? However, C can be interpreted alternatively as the movement of points on the surface z equals to 4 minus x squared minus 2y squared. Moving along, or against the direction up. So basically, now if you think about traveling along the purple curve, so let me just do the illustration right here. So basically, you have a purple curve like this in the xz plane, right? So if you do the parameterization, it's just going to travel from the top to bottom like this. Okay? But here we're just saying, okay, it will be essentially the same idea if we are just trying to move within the xy plane from the black point only along the x direction. Okay. So essentially, let me erase the point. Yeah, let me not erase the point. So basically, the idea here is that let me make it. So that's even more. Okay, make it even fatter. So basically, we can move along this direction. So that's I, right? Or if you go along the negative I direction, that's this direction. So maybe the magnitude is slightly larger than 1, but that's here this is just an indication. Yeah, right. So this is the indication of the direction. So this is definitely a 1. So negative I is this direction. So the purple curve in this sense is actually the movement of the black dots on the top, right here. If you just move along, if you just move when you just change the xy input pair along the direction I or negative I, so your black point will just move along the purple curve. So that's the concept right here. So now we just treat this like a fresh concept, and here we want to compute the rate of change of the function z equals to f of xy. Of course, it has the same definition along the direction I at the point x equals 1, y. So we just do it in a systematic way, starting from this concept of the rate of change along a direction. So what do we need? We just need we want the instantaneous rate of change. Okay, so the idea here is that we approximate by the average rate of change when you slightly change the inputs, and then we just push that tiny little change to 0. Okay, so here this is not really difficult, but we just want to put it down. So changing variable, now it's going to be starting from the point 1, 1 to the point 1 plus h1, because here we're just moving along the I direction. Okay, so it's going to be a move h units along I direction. Okay, so essentially, this is exactly the xy plane where we have the point 1, 1 right here. But then we're just moving along the direction I. So we have changing variable, and then we have the changing output, change in functional value. And the change is, of course, just the letter output minus the product, right? So it should be f of 1 plus h1 minus f of 1, 1. So the rate of change is the change in output over the change in input. And you can see where we're going, right? So we can just define the instantaneous rate of change by taking the limit when h goes to 0. So yeah, let me finish this line before I let you guys go. Instantaneous rate of change is exactly the limit when h approaches 0 of this fraction that we have. And we know by definition, this is what? This is f sub x at 1. Basically, if we were starting with the direction along I, okay, like this, then here we're establishing the formal process to analyze the instantaneous relation. So we, in the end, we get to the point where we have epsilon x to be the partial derivative at the point that's gonna be the instantaneous rate of change when you are traveling along the direction I, right? Along the x-axis. Okay. So this is definitely standard. But then later we're gonna ask, okay, what happens if we have a different direction? So here, mark. F sub x at 1, 1 is the instantaneous rate of change of our function f of xy at the input point 1, 1 along direction I. Okay. And similarly, if you just switch to f sub y, that's gonna be the instantaneous rate of change from the same function at the same point. That is along direction j. So here, let me copy the figure above about the direction that we are looking at in the domain. Okay. So basically, we establish from the direction I. Okay? And then of course, we covered the direction j. If we look at the partial derivative right y for the function, right? And then in general, we're gonna ask the question, what happens if we choose a direction that's different from I and j, but as a unit vector, let's say something like this. Wanted to get the vector, but I accidentally erased everything. So let's say this is the direction u. Okay? So I and j, they're just unit vectors. They are vectors along axes x and y respectively, but they have the unit magnitude, right? And here we're asking, what if now it's so it's bold. What if we are concentrated, we are concerned, we are concerned with the instantaneous rate of change of change along a different direction u. So this is the question we have in mind. And then we just do the exact same kind of analysis following. So basically, we do the change along the direction where we move along that direction by, let's say, h units. And then we just gonna analyze. Okay. What will be the instantaneous rate of change? So we just need to put down the question a little bit more openly, but still it's following along the same form of the previous questions. Okay, so it's the instantaneous rate of change of same function f of x y. Along direction. So now we need to put down u. Okay, so u is, of course, u is lying within the xy plane. It's an arbitrary direction, but it can always be represented as a combination of I and j. Right? Let's just denote it as I. It will be ai and bj. And assuming that u is a unit vector. So now instead of going along the direction I in the previous analysis, now we are going along this direction, okay, ai plus bj. So still, this is the change in variables. And now we are changing both components, right? So let's say we start with 1, 1 again. So 1, 1 is the point that we start with. And then we go along this direction u with h units. Okay, so it's now gonna do it. So basically, this is a unit vector, so we're gonna travel, this has a unit magnitude, and then we travel h units, it's gonna be h times this vector, right? So that's in addition to the 1, 1 coordinates. So it's gonna be 1 plus ah, 1 plus bh. Okay, so this is going along this direction u for h units, right? So that's the change in the input. And then, of course, we do the change in output, in function value. So it's the same process as before. So we have the input pair, 1, 1, and then the latter input pair. Then the function output is gonna change as the latter minus the previous. Okay. And then if you look back at the process we have done, then we just do the average rate of change in this interval, and then we take the limits, right? So instantaneous rate of change is going to be the limit where my increment h goes to 0, and I'm just taking the limits of this slope of secant, right? Average rate of change. Okay. And now, so you see, this is now slightly different from what we have seen in the previous analysis. Now we have a, h, and bh increments in both x and y coordinates. Okay. So although this looks slightly different, but this is something we can handle. So remark. We can utilize chain rule, right? Remark. So defining G of h should be the latter output. So because now we are traveling along the direction AB, so here AB are parameters 1, they are input values, initial input values. So only variable here is age, right? So this is essentially just a kind of parameterize the x and y values. Okay. If you think about it, let's write down the evaluation of the limit. So when h goes to 0, we are looking at the limit of the average rate of change along the direction AB. And now, of course, if we express everything in terms of g of h, is going to be what? It's going to be the limit when h goes to 0. We know that the latter output is g of h exactly, right? But then the prior output is g of 0. Okay. So basically, when we don't move from the point 1, 1, then that's going to give you just f of 1, 1. Right? And now by definition, this equals what? This equals to g prime, right? So there's only one variable here, which is h, right? So this is the instantaneous rate of change of the function g at the input level, h equals 0. And then, okay, so that's good. So this is a trick we have done for several times, right? So basically, we write the original compositional expression in terms of a new notation, and we realize that this limit is exactly this compositional relation at g. So the rate of change of g. And now let's just think about what happens. So g is actually defined by what? So basically, the output is f, right? But now x and y, they are now relying on h, right? So that's the tree diagram we want to establish. So basically, this f of xy. So when we were starting with the example, let's just think about this specific case where this f is 4 minus x squared minus 2y squared. So this is the well, multivariable function f, right? But here we specify that x must be 1 plus ah. It's a linear function in terms of h. Y is 1 plus bh is another linear function in terms of h, right? So now we have this parameterized case. So now we're doing the rate of change of f in terms of h. So there are two passes, right? So let's write it down. So we have del x dx dh plus del f del y dy dh. Okay. So g prime in terms of h is now the chain rule. It's actually chain rule case 1, right? And here we just want to evaluate when h equals 0. And then, well, everything is just going to be standard. Okay? So we write down the partial derivative. So we have on the upper right corner the function definition. So if you do del f del x, it's going to be negative 2x. Right? So 4 minus x squared minus 2y squared. That's our function here. So if you do the partial derivative of x, it will give you negative 2x. If you do the partial derivative of y, it will give you negative 4y. Okay? And here we are multiplying by dx dh. Now dx dh this is the linear function in terms of h. So if you do the derivative, it's going to be an a, right? A right here times a. And now similarly for dy dh is going to be a constant b. And then add up. And here we realize that when we are evaluating at h equals 0, we are also evaluating the x and y values, right? So when h is 0, x must be 1, and y must be 1. So by the parameterization. So and now, okay, we see this is well. If you think about one of the previous examples that we have done about this kind of bivariate function, we are just going along the direction well the AB along we'll call H units. This is something we have seen already. So we just plug in. Okay, so this is exactly negative 2a minus 4b. Now this is a scalar value, but we see that this highly relies on the direction A and B. Okay, so A, if you think about this, is the coordinate of the unit vector u, and this B is the y coordinate of the unit vector u. Right? Yes.
Why do we know that x equals 1 and y equals 1?
Oh, here, that's exactly, this is a very good question. So why do we know the x and y values? That's right here. So basically, this part is the x coordinate, this part is y coordinate. So yeah, let me. So we started with the function, right? We started with the function f of x, y, but now we are looking at this little g, which is basically saying x is 1 plus ah, b y is 1 plus bh. That's exactly what.
Okay, I get it.
So to put any other questions? So it's fortunate that we have seen this example in the previous section. Okay, so now this doesn't stand out that much. So now depends. So we just give the comment in words. So we see that the final value, this instant derivative change depends on the vector u. So this final instant derivative change relies on A and B, which are the coordinates of this unit vector u. And then, well, you can further even mention that this is what this is actually the vector -2, -4, starting with AB, right? So that's definitely a valid observation. But here, let's define. Definition. We define the directional derivative. So this is a calculation of the direction. So the directional derivative of a function f at any point x0, y0 in the direction of a unit vector we still call it u as ai plus bj. So basically, for a general function, the little f starting at the general point x0, y0, and we give this unit vector u as the direction that you're traveling along, then we define the directional derivative to have the notation cap d sub the vector u of our function at the point x0, y0. So this is the notation of the directional derivative. Okay? But then if you think about the definition of this instantaneous rate of change, that's the exact same old definition that we have seen from above. So it's so this is the limit when the change in along the direction which is h approaches 0. So this is the change in our output which is of course the latter output minus the prior. Okay, so this is changing the output, right? And changing input is h. Okay, so h units along the direction u. So to formally write down the definition of the instantaneous rate of change is going to be this. And then before we just repeat the process in the previous remark, I'm gonna establish the figure for the same elliptic paraboloid. So if you recall, basically we have this this kind of shape. So we are not really utilizing that same figure from the previous examples in the sense that those figures were in the along the direction I and j, right? So when we talk about the partial derivatives, but now we are choosing a general direction, so that's slightly different. So here, this is still the point 110, and 111 is the output point right here. Okay. So here, let me say this is 110, and that's 111. But now we're moving along some direction other than I and j. So let's say let's say something like this. Let's say this is u. So basically, what's going on here? So this direction u will determine a plane that's actually vertical to the xy plane. So if you think about this, yeah, let me just do this. So well, you somehow need to imagine that the dashed black line and this vector u, these two directions will form you that plane that's perpendicular to the xy plane at the bottom. Okay, and then it will intersect the surface on the top. So it will intersect and get you some curve. Let me put it in a little bit more a bolder red. So it's something like this. Okay. So it will still be a quadratic thing because your function here is quadratic, right? But then it may intersect. Probably somewhere here. Okay. So basically here I'm extending the direction u. It will probably intersect the surface at a certain point on the xy plane. So this is so basically if you go along the direction u, you will be traveling from the black point along this direction. Okay, if you go along the negative direction of u, it will just travel along the opposite direction, and then this is a quadratic curve that you're traveling along. Okay, so that's the idea. But now, if you think about the instantaneous rate of change, what's that? That's actually, so we have a curve, and then we can draw the tangent line going through the black point right there. Okay. So the picture doesn't look really perfect, but you get the point. Okay. So that's the slope of this tangent line is the instantaneous rate of change. Okay. Slope of tangent again. Okay. Slope of tangent. Yeah, well, probably I want to make the curve a bit nicer so that it doesn't look so ugly. Something like this. Okay, so yeah, well, this looks a little bit better now. But that's the idea here. So it's again a slope of tangent. Remark. So in the following remark, we're just gonna put down some more formal calculations regarding the function f and the data point x0, y0, and an arbitrary direction u. But it's still the same process. Okay. So if we define, so here once again, this expression here only relies on h, right? So we still call this a g. So this is g of h equals to f of x0 plus ah, y0 plus bh. Then we realize, so this is the latter output, then the prior output is exactly g of 0, right? So the directional derivative, so cap d sub u of f of x0, y0. So the same thing. And then the first step tells you we're just doing the derivative dg dh and evaluating the h equals 0. Right? So this is an instantaneous change at the point g of 0. Right? And then the similar process tells you, okay, so dgdh is, this is the general case one, that this is the diagram, so I'm not gonna repeat the diagram, but basically we have f sub x. So instead of doing del f del x, we are writing f sub x of x or y as the partial derivative function, multiplying by dx dh plus f sub y of xy, multiplying by y dh. Okay, so that's the chain rule, case one. And then we evaluate h equals 0. And of course, so that's the x portion, that's the y portion. Right? And then we evaluate. We realize that when h equals 0, x must be x0, y must be y0. So here f sub x. So the partial derivative. So here we don't really. In the previous remark, we have the explicit expressions of these partials, right? But they are not that critical. So dx dh is only a, dy dh is only b, and we plus. And then h equals 0, and at this point we have x must be x0, y must be y0. And the reason of this evaluation is exactly because now here at the point h equals 0, ah and bh are gone, right? So it's good. And then we're done, right? We're almost done. So here we plug in, so there's no h anymore, there's just x and y, right? So this is exactly the partial derivative at the point x0, y0, starting with multiplying a plus f sub y of x0, y0 and b. Okay, so this is the calculation, the formula for the directional derivative. So this we can state as a theorem. If f of xy is differentiable, then for any unit vector little u equals to ai plus bj, we have the following formula. So it's the directional derivative equals to the lines right above. Okay, so we have the directional derivative along the direction u of f. So so here we just replace x0, y0 as just the xy pair. Okay, so that can be done, right? This equals to f sub x at xy times a plus f sub y xy. Okay, so here we just replace the circled xy pair to be the general x vector. Okay. Because this is true for any point x1. But then we can rewrite it as what? We can rewrite it as vector f sub xi plus f sub yj, starting with u. Right? Right. So is it? Okay. So now we see, okay, the directional derivative, that just relies on the partial derivatives as a vector. And then once we calculate this vector, we just start with our vector that we start with, the unit vector u. Okay. Remark. This is the bivariate function case, right? But in general, if you have the 3 variable or even n variable, it's going to be the same kind of process. Okay, the definition can be extended to functions of many variables. For example, here we give another definition. The directional derivative of a, let's say, a 3 variable function f of x, y, z at the point x0, at the point x0, y0, z0 along direction along the direction of unit vector let's say u. So now here we have three variables, right? And then for unit vector, it has to have 3 components. Let's say a, b, c. So if I want to define the directional derivative here, then it's going to be the same definition as the limit of the instant temperature change. Right? So basically, still we're gonna do the aggregate change when we walk along this direction u by h units. Right? So it's gonna be the change in input, which is h units. The change in output is f of x0 plus ah, y0 plus bh, d0 plus ch. So that's I need the line to be a little longer, but you get the point. Okay, so we just introduce one more entry to the definition here, and of course, you can expect that the final result for the formula of the directional derivative is going to be the same idea. Okay? Theorem. If f is differentiable, then the directional derivative of the function f at the point x0, y0, z0. So in the previous parts, we are doing f sub x, and f sub y, right? So now let's do the Leibniz notation. This del f del x evaluated at top pole x0, y0, z0, multiplying a plus the y evaluated at the point times b, finally plus. So these are the original 2 terms in the directional derivative, right? Here we have the third component. We have the third variable. Okay, so but we just fill out everything. multiplying C. And then now if we treat the tuple x0, y0, z0 as a general point, x, y, z, then we can also write the functional notations. So treating as functions of x, y, z, then the directional derivative along u of f of x, y, z, right, at any point is gonna be, so here we just need to just abbreviate. So we just omit the tuples, right? So here this is f sub x times a plus f sub y times b plus f sub z times c. Okay? And then if you want to put down as the dot product, it's gonna be the vector that's having the components of f sub x, f sub z, starting with our vector u, unit vector u. So now this is of course parallel to what we have seen from the bivariate case, right? But now this part, we see this vector that consists of the partial derivatives, the first order partial derivatives, right? So this vector is very important. So this is the vector that's called the gradient. That's our second part of the section. Definition. If f is a function of three variables, then the gradient of little f is the vector. So we said it consists of all the first order partial derivatives, right? But now the notation of this is a upside down triangle, which is called nabla of f, and nabla f. Let me just write it down right here, nabla. So this is the pronunciation. I want you to make it as simple. Alright. Nabla f equals to the vector that has the partial derivatives as the components. So this is the three variable case. Okay. Remark: if f is a function of two variables, then of course there will be two first order partial derivatives, right? You put it as a vector, then that will still be the gradient. Okay. Then nabla f is gonna be just well, if I want to put it as the in terms of the standard basis, this is del x r plus del y j, right? And the same idea. And if f is having n variables, if we have f of x1 all up to xn is a function of n variables, then the same idea, right? So nabla f is gonna be the gradient, which is the n component vectors, right? Every component, the ith component will be the first order partial derivative of the ith variable. So it's gonna be del f del x x1, del f del x2, all the way down to del f del xn, right? So very standard. And now, as now we have introduced the gradient as nabla f as a vector, right? Then we can simplify the formula for the directional derivative. Okay? Another remark. If f is differentiable, then the directional derivative along the direction u of f is exactly nabla f talking with the vector u. Right? So nabla f has n components. U also has n components, where n is number of variables that you have to the function. Okay. Example. So let's say, so find the directional derivative of f of xy and equals to x squared y cubed minus 4y at the point 2, -1 in the direction vector v equals to 2i plus 5j. So these are all the information that we need. So the function f, the point xy pair, right? And finally, the direction along which you are traveling. But here we are giving the vector v, right? So we're not really giving a vector u, since this v is not a unit vector. So we just need two things. We just need, okay, the gradient at the point, and we need the unit vector along the direction v, right? So we have the gradient nabla f of xy. So there will be two components, del f del xi plus del f del y j. So this is the gradient vector in general for any data points, for any xy pair. So now we just do the partial. So it just should be now really standard, right? So x squared, so the function has only x, the x expression in the first term, so it's gonna be 2xy to the 3. So that's the partial derivative of x, right? Times I plus. So now both terms in the functional derivative have y, so that gives you a sum. So 3 y squared, and we have x squared as the constant multiplier there, minus 4y gives you 4 when you're taking the partial derivative, so that's in front of j. So the gradient is now I would say a bivariate vector, right? So both components are bivariate functions. Now we need to evaluate the points. Okay, so at 2, -1, the vector, the gradient vector -1. So we just plug in. Okay, so you should get 4 of -4. So that's for the I component, and then we have 3 times 4 squared, that actually 3 times 4 times 1. Okay, that's 12. That's 8. So that's just the evaluation. So now we get this part, we get the vector part, right? We get the gradient vector part, and then for v, we need to normalize it and get the u. In the direction of v, the unit vector is basically the vector u that is v over its magnitude. Right? To normalize, we just divide by its magnitude. So this is 2i plus 5j holding over the magnitude, which is the square root of the component squared. So that's what? That's 4 plus 25. Right? So we have 2 over the square root of 29 plus 5 over the square root. That's good. And then we just dot. Okay. Hence, the directional derivative, so d sub u of f at 2, -1, we just dot the gradient at the point with the unit vector that we calculate. So this is -8 over square root 29 plus 8 times 5, that's 40. So here we can just keep the radical in the denominator because it doesn't really affect. So once you do the dot, you will get that. So now we see that when we calculate the directional derivative, we don't really have to do the limit definition anymore. So it's just a really systematic process. Okay. Another example, if we have f of x, y, z. So now let's say the function is defined as x times psi of y, z. We want to find the directional derivative of f at the point 1, 3, 0 along the direction of vector. So now we are giving a v again. We are giving a direction that is not a unit vector. So I plus 2j plus k. So the same strategy here. So we just compute the gradient and then we evaluate the point and then we get the u and then we dot. Okay. So we have nabla at a general point x, y, z. Just list the partials. Okay. So when you do the partial with respect to x, so that's just gonna be sine of y, z. When you do the partial with respect to y, okay, it's a composition. So it's so x is constant multiplier in the front. So z is the constant multiplier in front of y, right? So basically the derivative of delta is cosine. And then we evaluate that the yz, and then we multiply by the derivative of the inner. So it's z in front. Okay. And then for z, for the partial derivative of z is the same thing. So x is the constant multiplier, sine gives you a cosine, plug in the inner, and multiply by the derivative of the inner. So evaluate at the point 1, 3, 0, and we realize that z is 0. Okay, so it tells you the first component and the second component are all zeros. Because here, so z is here, and z is also here. Okay, the only non-zero entry is xy times y. Xy gives you a 3, and then cosine of 0 is a 1. 0, 0, 0. So now we get the gradient evaluated at the point. So that's good. And now we just need to play with the unit vector u. Okay, so the unit vector along the direction of v is still it's gonna be the u as the vector v over its magnitude. So this is so let's put it in the double form. So it's 1 to 1. Whole thing over the magnitude, the magnitude which is square root of 1 plus 4 plus 1, the component squared. And we see that the denominator is the square root of 6, right? So this is 1 over square root of 6, 2 over square root of 6, 1 over square root of 6. Hence, we got d sub u of f at 130 is gonna be okay, we realize, okay, only the last component is actually doing n, right? So it's 3 over square root of 6. Because it's gonna, it's 0 for the gradient. So this is square root of 6 over 2, if you want to simplify. Right. Now let's see. We are talking about now the geometric meaning of the gradient. So here, we do have a figure about the directional derivative, which is the instantaneous rate of change of the function along a direction, right? But here, we also have a figure, so let me put that down. Recall that the directional derivative of a function is the instantaneous rate of change of f along direction u. So let's look at one of the previous figures and copy that down. So basically, we chose the direction u, and then along that direction we got a slope tangent, right? So basically, if you think about this figure, actually helps you to see certain things. For example, basically, if you go along this direction u, you are actually slightly decreasing your function, right? Because essentially you're traveling along the red solid curve. Okay, so and the slope here looks to be negative, so that tells you, okay, going along the direction of u, your function value is decreasing, like this, right? But then if you choose to go along the negative direction of u, then you are just going the opposite direction, which is increasing in the along the same line, right? So basically, that instantaneous rate of change is representing that, right? And here, basically, this looks to be a slide that well descend in a way, right, along this red curve. Okay, so now if you think about it, if you change the direction of u, you can see, okay, looks like if we go along this direction, u within the xy plane, so that's walking up the hill, right? That's something like this. Okay. And if you go the negative direction like this, then you're going down the hill. So basically, you're trying to stay on the surface, right? On the function. Okay. So that tells you something about the sign of the directional derivative that you get. Okay. Note. So this is our surface, which is function graph 4 minus x squared minus 2y squared. Okay. And then the instantaneous rate of change is the slope of the red red line. Right. Note that, of course, if you change the direction of u, then you will have different, possibly different slopes of tangents. But then we can think about the maximum and minimum values, right? Because you know that the directional derivative is equals what? Equals to the gradient nabla f dotting with our unit vector u. Okay. So now think about this. So you have a dot product, and this by definition equals to the magnitude of the gradient multiplying by the magnitude of u multiplying by cosine theta, right? And what's theta? Theta is the angle between the gradient at the point and the unit vector u, right? And now you see this part is just one. This is a constant, right? So when you're at a point, you can calculate the gradient as a vector at the point. And then the magnitude is a constant, right? So the circle part is a constant. The magnitude of the unit vector is one. So the only thing that's changing if you change u is gonna be cosine value, right? And then, so this tells you if your theta, if your angle between the gradient and this vector u, if it's zero, then we have a maximized directional derivative. And of course, if theta is pi, then cosine is the most negative, right? So that tells you the maximum of the directional derivative occurs when theta is zero. That is, when nabla, the gradient, and the unit vector are having the same direction. And of course, that's possible, right? Because u is a, well, in our figure, u is a two-dimensional vector, right? And the gradient is also a two-dimensional vector. So how are you going to choose u to follow along the direction of the nabla? So you can think about just using nabla dividing by its magnitude, right? So that's it. So that's really simple. Therefore, the directional derivative is maximized when u is of the same, is of the direction of nabla. In such case, directional derivative of u, excuse me, the directional derivative along u of the function f is exactly the magnitude of the gradient. Okay. So, basically, if you think about that vector as the gradient for this function, let me zoom out a little bit. So basically, if you think about it, this is actually negative 2x, negative 4y as the gradient vector, and at 1, 1, you just have negative 2, negative 4, right? Negative 4 is exactly this direction. Okay. And now if you go along this direction, you're actually going up the hill, and it looks like the slope is the steepest, right? Like that. It's going up. Okay. So that's exactly what it means by saying you are just having the maximum directional derivative. Okay. And of course, if you go the opposite direction, it's gonna be the most negative directional derivative, okay? Going up the hill, going down the hill, with the fastest, with the largest instantaneous change. Theorem. Suppose that f is differentiable. Then the maximum value of the directional derivative of function is the magnitude of the gradient, and it occurs when u is along the direction of lambda. Okay. So here, let me put a bracket. So basically, u equals to lambda f over its magnitude if the gradient is not a zero vector. So here, as long as it's a non-zero vector, then you can calculate the non-zero magnitude and then do this scaling, right? But if you have a zero vector, then you cannot really do the scaling. But then u is just also the well. Let me think. So u is a unit vector, then it will not be the direction of a zero, right? So that's really special here. So that's why we don't really put it down in the theorem, but as a side note, right? Here. Remark. So basically, you have a maximum directional derivative that is exactly the most positive one. Okay, so lambda is the direction along which f increases the fastest. So it has the most positive instantaneous rate of change and along that direction. And of course, if you go against that direction, then you have the most negative instantaneous rate of change. Example. Suppose that the temperature at the point x, y, z in space is given by the following function, cap t of x, y, z. This equals to so this is a fractional function, and this is or you can call it a rational function. Basically, it's a constant 80 over 1 plus x squared plus 2y squared plus 3z squared. So we have this cap t where cap t is in degrees Celsius, and x, y, z are in meters. So we now know this function, and we are looking for the direction along which it the temperature increases the fastest. Okay, so in which direction does the temperature increase the fastest at a particular point, at the point 1, 1, -2 in the space. And also we want to know what's the maximum rate of change, okay? What is the max rate of change? So basically, this is utilizing this previous theorem and the remark at the same time, right? So basically, we are given the point 1, 1, -2, and then we just want to look for the gradient direction so that we go along that direction. That will be the direction along which our function increases the fastest, right? And then the magnitude of this directional derivative is exactly the magnitude of the gradient. Okay, so the most important thing here is to calculate the gradient. So and we also need to realize that this is a fractional function. So well, it's if you do the partials, then every component we just need to do the chain rule. Alright. So let's calculate the gradient cap t is gonna be, of course, del x del t del xi plus del t del yj plus del t del k del zk. Okay. So there are 3 components. We need to do the 3 partial derivatives, and we need to do it carefully for the question. Okay. Right. So let's see. We have 80 over 1 plus x squared plus 2y squared plus 3z squared. So if you're doing the partial derivative of x, and you notice, okay, x is changing, and y and z are treated as constants. Okay, so essentially you have a constant over 1, well, another constant plus x squared holding to the -1, right? So if you have a fraction, it's always recommended that you write it as a negative exponent and then do the chain rule. So if you do that, then what do you have? You have 80. This is the denominator to -1, right? So that gives you -1. That denominator to -2. So this is the derivative of the outer function. The outer function is just the denominator raised to -1. So the derivative of the outer, plug in the inner. I need a little more space. And then you need to multiply by the derivative of the inner, which is 2x, right? And then I. Okay. So we're doing this in a really systematic way because now if you think about it, the outer function is going to be the same for x, y, and z. Okay. Because the fraction is still the same fraction. The only difference between x, y, z is that you have x squared, but you have a 2y squared or 3z squared at the denominator. So we can slightly cheat by copying this common part. So if you're doing the partial derivative y, it's the same expression in the front. And then the derivative of the outer evaluated the inner, and then you multiply by the derivative of the inner. And now for in terms of y, that's just 4y j, and copy that again. So it's gonna be 6z, right? Okay. Okay. All right. So we have this fraction in the front, so that okay, they are in common. Okay. So and also you realize that we really want the direction. So the constant multiplier in the front does not really affect the direction. So the direction is important, and the common scalar in front of it is not really important. Okay, so only the circle part in purple is important. Okay, so we have that fraction in the front, and then we are we are multiplying. This is a scalar multiplying by the vector what? 2x, 4y, and 6z. Right? You can also factor out that 2 that are in common. So if you want to write it out, this is a negative. So 2 times 80 is 160 over 1 plus x squared plus 2y squared plus 3z squared, all things squared. I need the fraction not to be a little bit longer. But then, okay, I factor the 2. So the vector here is going to be xi plus 2 yj plus 3z. Okay. Right. Okay. So now we do know the gradient at any point x, y, z. Okay. So let's look. So that's this is something you should be proficient by now. So the partials. And now we just plug in the points 1, 1, negative 2. So if you want to get the unit vector, so this is going to be this vector. You plug in 1, 1, negative 2, and then you will get the direction, right? Well, but also you need to be careful. Here we have a negative scalar in the front, so you definitely want to consider both these. So let's just plug in the numbers. Here, we are looking at the gradient of the function at the point 1, 1, negative 2. So this is negative 160 over. So we have what? We have 1 plus 1 squared is 1. We have 2 times 1 squared is 2. We have 3 times negative 2 squared, so 3 times 4 is 12. Okay. So you see, in the denominator we have what? We have 16 squared, which is nice. And then x and y are 1s, so we have I, 2j, and then we have z is negative 2, so it's minus 6k. Okay. So you can see if you only think about the direction, then okay, so the vector in the bracket is the most important. Okay, and then we have a constant scalar, but the scalar is a negative number, so that's something we need to be careful about. So this is negative 160 over 16 times 16, and then I plus 2j minus 6k. So this is what? This is negative. So we cancel out the 16, that will give us 10 over 16, which is 5 over 8 along the same direction. Okay, so this is the direction of the gradient. Okay. So here, well, we are not really asked to look for the unit vector along this direction, so we don't really need to normalize. So here we just need to say that we need to go along the direction that is parallel to the gradient above. And of course, then the maximum rate of change, instantaneous rate of change, is the magnitude of this vector. Okay. So here we are asked to calculate when we are going along the direction of the gradient, what's the instantaneous rate of change, right? So we need to calculate this magnitude. So basically, we just calculate calculating the magnitude of this. And what do we know? We know that the constant multiplier in the front can be taken out outside of the magnitude if we get the absolute value of that scalar, right? And then we still need to do the magnitude of the remainder direction, okay? But that's not really difficult because we have just what 1, 2, -6, right? So it's the square root of the sum of squares of these components. So 1 plus 4 plus 16, actually 36, 6 squared. So this is actually 41 in the under the square root. And then, well, this is the accurate value, right? But then if you do it as a calculator, approximate the value of the square root of 41, this is approximately 4. And then we just need to answer that this is in degrees per meter. And that's it. So basically, here we just this is the implication that's if we go along the gradient direction, that will be the fastest increment. If we go along, well, of course, if we go along the negative gradient direction, that will be the most negative instantaneous rate of change. Okay, so this is the minimum rate of change. Okay. Any questions so far? Right, so now the last concept of this section is about gradient ascent. So actually now at the point, or for whatever point that is on your domain, you will be able to know, you will be able to calculate the gradient of a given function, right? And then if you want to, so there's a really simple strategy to maximize the functional value. So basically at any point you just go along the gradient direction with a certain step size. So if your step size is not really large, right, then you're guaranteed to slightly increase your functional value. Okay, so basically this algorithm is just saying, okay, calculate the gradient, go along that direction for small step size, and then you just you're at the next point, and then you calculate the gradient, then this next point, and then you go along the direction of that slightly. So this is like iterative method. Okay. To illustrate, recall that Nablab is the direction along which f increases the fastest. So let's look at a function that is having two variables, and we are looking at counterverbs. And move the axis a little bit lower. So we have x, y axes, and then now let's just look at some counterverbs. So counterverbs. So basically, let's say we have the lowest level. This is level of f of x, y equals to let's say little k. And then we draw another one that's higher. So this is level k plus 1. And let's say we have the highest, that's right here in the middle. Let's call this level k plus 2. Right, and now let's say we start at a point right here, it's x0, y0. So basically, here we have this function. That's z equals to f of x, y. Okay, so for this function, we are given these counter curves, that's as a representation of our functional relation. And here we want to start at the solid point, x0, y0, and we want to increase the function value, right? So here the strategy is the following. So we want to go along, we'll walk from the solid point, and we do have a choice of several directions, right? We can possibly go like along this direction, we can possibly go along this direction, we can possibly go along this direction. But then we need to think, okay, so if we slightly walk along these directions, and also we possibly have this direction, right? So we slightly go along these directions, and we of course want to pick the one with the largest increment, right? So then here we just choose the gradient direction. And of course, if you think about it, this direction is actually kind of tangent, right? It's kind of tangent to the counter curve that you're staying on. So what does this counter curve tell you? So the counter curve tells you your functional output is always k, right? So if you draw a tangent line, that's actually the direction along which your, so let me sketch it right here. So if you have a tangent line that you can sketch for this counter curve, then if you go along that direction, then you're saying, okay, my functional value is staying the same, right? And then so you're gonna choose the gradient direction, and as a fact, the gradient direction is actually perpendicular to the dashed tangent direction. Okay. So that's actually the direction that you are guaranteed to increase your functional value if you slightly walk along that direction. Okay, so that of course, to think about a better illustration, we can think about the graph. So we have three counter curves, right? So the graph, so the middle counter curve is actually the output level that's highest, and then the lower one is gonna be a counter curve that's lower, and of course the most the largest counter curve is actually the lowest, right? So if you're trying to sketch the function graph, then this looks like a hill. Okay, so this is the graph of z equals to f of x y. Right, but then we are trying to walk up the hill, right? When you start from some point like this right here. Okay. So that direction with the fastest increment is actually the direction that you are walking up the hill, and with the largest slope. Okay. And then if you, of course, if you're going along the level curve, right, the counter curve, that's just gonna be along the counter. So as the so to put down the observation that we have a little bit earlier about the relationship between the tangent and the gradient, I'm just gonna put it here. So at the point x0, y0, the gradient should be perpendicular to the level curve. And later we will see that exactly your level curve, the tangent line here is actually what's that called? A linear approximation. Okay. That is saying, okay, at this, on this line, my function value will stay the same. So it will be a tangent line here, and if you have a higher dimension, it's gonna be a tangent plane, something hyperplane. But then the gradient is actually the normal direction of this tangent. So basically, if you go along the gradient direction, it will slightly increase your functional value, and that's actually the fastest. And then we can think, and then we can talk about the gradient ascent as an algorithm. So let me draw a few counter curves as an example. So let's say this most outer is the 0 feet level, elevation level, and 1000 for the one in the inner one, and even more inner one, you have 2000. And then let's draw a few more. 3. So essentially, when we try to maximize the functional value, we just want to go uphill, right? But then to do an iterative computation, what do we do? So let's say we start at this point, and then, well, if you want to just graph, then what you can do is, okay, you draw the tangent line, right? So that tells you the direction that your gradient has to be perpendicular. So you walk along the gradient direction, and you will stop at some point, possibly. So in this example, let's just do it so that we just meet the next counter curve, okay? And then we just repeat, okay? So we get the tangent direction, and we get the gradient direction, which is perpendicular to your tangent line. And then we go to the next, and it just goes on and on. Well, it doesn't look that perfect, but yeah. Just goes like here. And then, so it's indeed an iterative process, okay? So there isn't really a lot to say, but computationally, that's what people do. Especially when if you have a complicated function, but you are able to compute the gradient, then they can automatically compute it with some programming language. But the idea is not really complicated, right? So you probably will get here, and then can even go further. So that's the black point. And then essentially we want it to get to a maximum that's possibly somewhere here. And this is what's called the steepest ascent method. So basically, at every data point, you just compute the gradient direction, and you just walk along that direction slightly, okay? And you just get to the next point, compute the gradient, walk again, and just repeat the process until you stop at a certain point. Okay? All right, so that's pretty much all you need to know about the gradient. And then the next topic is about the tangent planes and linear approximations. All right, so these are just conceptual, okay? So definitely not really required for the exams. But of course, this is highly important if you're talking about machine learning tasks that you are doing the gradient methods. Okay, so especially for large scale models. So the gradients are not really hard to compute. If that's the case, then you can always do this kind of gradient ascent methods or gradient descent if you are minimizing the function value.